Okay, so we're going to continue here. So far what we know is that Democritus discovered the atom, or at least proposed the idea of the atom in ancient Greece, but it wasn't believed. And then it took the alchemists and then the work of Lavoisier and Priestley in the Age of Enlightenment to then bring about John Dalton's discovery of the atom. That he said it was an indivisible, indestructible particle, all atoms were alike, and any atom that was different and of a different element was different, and then atoms came together in a very, very specific way. Sometimes it was always the same proportion, and sometimes they were different depending on what the atoms were that were coming together. Then we went on to discover that Faraday and Crookes had made some discoveries about electricity before in 1897, Thomson discovered the electron, and he discovered the electron using one of Crookes' cathode ray tubes. So the next person to make some discoveries was Ernest Rutherford, and in fact, Ernest Rutherford was a contemporary of Thomson. He was, in fact, Thomson's student. So we've got a couple videos for you to watch here in just a few moments. So we've got Rutherford, and Rutherford conducted experiments using radioactive particles that we know as alpha particles.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
So, Rutherford was quite confused. He saw these results and these things going straight through and some of them being deflected, and he wasn't sure what to think of that. Because it was solid matter, how could things go through?
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position, behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, and what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference.
Okay, so 2 years after wondering, Rutherford finally figured out what was going on. So we've seen the conclusion, we've seen what's happening, but Rutherford basically says, okay, so since this is a positively charged thing that's being shot at this, in order for it to bounce away and not go straight through, it has to be densely packed. It has to have a positive center. So instead of having this gooey, like ice cream-like stuff, it's got this hard center in the middle that's densely packed and positive. And he called that thing the nucleus, much like the nucleus of a cell. And the study of atomic particles was born. So this was the beginning of particle physics as well. So Rutherford's view of the atom changed what it was. It was a densely packed positive center or nucleus. The negatively charged electrons were somewhere outside of the nucleus, and the atom was made of mostly empty space. And so the big takeaways here are the densely packed positive center, called the nucleus, and the mostly empty space. We are made of empty space.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists, because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator, so he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil. See what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounce right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun. Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounce off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away. After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
So as you've been told, the model that Rutherford had the nucleus in the center here, like this one, and then electrons somewhere around them, kind of like the sun and the moons and things orbit the sun. So we see different kinds of ideas here. So then we go a little deeper and we get into Niels Bohr, who is actually, again, a student of Rutherford's. Okay, and Bohr starts looking into some things by looking at hydrogen gas. He energized it much like the cathode ray tube. He put some electricity through it and he created this beam. And then he looked at them from the spectral emission lines point of view. And so when we see that this is hydrogen, but we also see that looking through the spectroscope, we were able to see specific lines. So hydrogen would give off these lines. You can see this one line at the red. We see this one line kind of in the light blue. And sometimes that's seen as kind of a turquoise color. And then we see a darker blue and even a violet. Depending on the kind of spectroscope you're using, sometimes these two lines merge into one somewhere in between here, kind of as a purple. And again, this one kind of looks a little turquoisey. So we see this, and he's like, okay, I could see these four colors. I could calculate some things. And he started to understand that these particles were quantized, meaning that they came in discrete packets that could only be allowed in certain energy forms. And with this new information, he began to change from the solar system model to a model that is more like planets, a planetary model. And this is where we see the atom most often. So we see these different rings as the orbits, and so the further away the ring, the further away the electrons from the nucleus. This represents the nucleus. And so the Bohr model is born. Unlike Rutherford's model that all of the electrons were like where the Earth is all of the time, somewhere out there. This is about the different orbits of all of the different planets, which is why he's given credit for a solar system model. Okay, but the problem is Bohr's assumptions only worked for hydrogen, only. So he knew more work was needed. So along the way, we get to Erwin Schrodinger. And what Erwin Schrodinger and his contemporaries, Heisenberg and a few others, figured out is that, yes, in fact, we had to look at the atom from a different point of view. We couldn't use classical physics, that classical Newtonian physics. We had to look in a different direction. And so we looked at electrons as waves instead of a discrete particle. And when we started looking at that, Schrodinger was able to develop a mathematic equation. The basics of this equation look like this. Now, you're probably not very impressed, but this function is called an eigenfunction, and it's basically a little higher level calculus. And you're like, oh no, higher level calculus. So it can be difficult to understand because there's more to it. So when we start looking at this, there are three pieces, three different distinct things that I can tell about this. And these are the eigenfunctions, or the functions that tell me about it. And all of this other stuff is information that helps us understand more about those things. But guess what? You don't have to understand the equation. What you basically need to understand is there are three basic facts. And we're going to be getting more into this when we get into the next unit and we start talking about the quantum model. Because this is what it really is. So this is what it basically boils down to. This is really our present day view of the atom. The atom is this thing that has this densely packed nucleus, but then the electrons are found somewhere outside of the nucleus, and it's more dense toward the center, but there are some that are found sometimes further out because we don't know where they are all the time. So there's a lot of question marks here, but I think it's a pretty good question mark to have. And so then finally, we've kind of alluded to this. James Chadwick, along with Ernest Rutherford, because Chadwick was one of his students, discovered the last particle, the most elusive particle because it was not charged. They discovered where the neutrons were because the protons couldn't account for all of the mass of the atom, and so they had to explain that. And so they used radioactivity and bombarded beryllium, and the particle that was released was neutral. And they went, okay, hang on. it has the mass of a proton, it's neutral, we're going to call that a neutron, and now they found the missing mass. So, in essence, this is the most accepted view of what the atom is now. It came from this idea that it was indestructible, indivisible sphere, into this idea of the plum pudding where there's this goopy stuff and electrons kind of scattered throughout, to this idea that there's a densely packed center and everything is kind of on the outside running around that densely packed center in the same space, to a solar system model in which we have things, electrons running around the atom in different levels, like a solar system. And then we have now the electron cloud model. So we can see where we've come. We will get more information to understand these progressions, but these are the basics of the atomic theory, and you'll be using them to help create your atomic history timeline.